Hello, everyone. So today, one of the highlights of the class, the free energy. So we worked quite hard last time to define the characteristic polynomial, see how it behaves with respect to fundamental domain enlargement, for example. And now we'll have the reward. So you remember in the introduction, to the class, I had asked one question: can one compute something like this quantity when Gn is a sequence of is an increasing sequence of graphs. So that was a question that I had asked, and of course this is a very natural question because it's, in particular, if you set all the weights equal to 1, then this is really the exponential growth rate of the number of perfect matchings on the graph. So it's a very natural question to ask. And of course, the first problem that you have when you ask this question is what kind of sequence do you take as sequence of larger and larger graphs, increasing sequence of graphs? That we work on the torus. We have natural sequences of graphs. Namely, as I explained last time, you start with one toroidal graph. You start with 1 that you call G1, and then you just make copies of them. So this would be G2. Etc. So not only it's a natural way to make your graph bigger and bigger, but the nice thing is that to some extent all the information is already in G1, right? The G1, which is it's a finite amount of information, you have some finite graph. This contains all the information. So you might think hopefully then you can compute the free energy just from G1, and this is exactly what happens. So it's a theorem which is due to Kenyon, Okumkov, and Sheffield in 2006. Sorry, first I want to give the definition actually because, sorry. So definition. The quantity, so in this setting, I want to denote by log z the limit, the corresponding limit here, or almost this limit, so it would be the limit for n goes to infinity, 1 over n squared times log of c gn. So this quantity here is called the free energy per fundamental domain. Okay, is called the free energy basically it's the same thing as this, almost. Okay. And now I can give the theorem. For any, so weighted bipartite toroidal graph G1, the corresponding free energy per fundamental domain is given as follows. We have that's it. So it's very remarkable. So it means you start with your G1, which again is just a finite amount of information. With this G1, you compute the characteristic polynomial in the same way we did and last time, and you did in homework. You have this polynomial. Well, you make the double integral over the unit torus of this thing, and that's the free energy. So maybe just as an example, if you take the square lattice, so if you take the square lattice with this fundamental domain, so with x and y's, what do we compute? So what do we get? We get something like log z is equal to 1 over 2 pi square. So now I express the integral slightly differently. And so we had computed this polynomial, and we had something like, so x squared plus x squared cosine phi plus y squared sine psi. You can check, you just take the computation we had made, and that's what you get. And in particular, if you set x equal 1 and y as well, then we get log z, maybe I can write this as a function of xy. This is equal to 4 times g over pi, where g is Catalan's constant. So this gives back basically the result of Castelline that I had mentioned at the very beginning of the class. And okay, this is an exercise, exercise 1. And maybe C also. So for the hexagonal lattice, it's also an exercise. It turns out in these two cases, you can really express this as a single integral. And okay, so this is also. Okay. So let me give the proof. So the proof is quite, well, we have everything in place, almost everything in place for the proof. So, so I'll just start with the notation. Set, so I want to write this, I want to take this notation, just because I will use it many times. Okay, what do we have? for any theta and tau, what do we have? Let me write z theta tau n. So by definition, this is the determinant, the absolute value of the determinant of kn minus 1 theta minus 1 tau. Okay, now comes a slightly redundant step, but since I always talked about Pfaffians and not determinants, so let me just write this as the Pfaffian of some Castelline matrix. That's a Castelline, well, this is the upper right part of a Castelline matrix. Its determinant is the same as the Pfaffian of some Castelline matrix for Gn. Okay? Now, absolute value. So this is the Pfaffian of a Castelline matrix is something of the form sum over all Dimer configurations of Gn of some sign times the weight. So since I might have some signs that are not 1, this is, well, this is less or equal to the partition function. Now the partition function, we saw that was, so this is really equal to the, I mean, that's given by the Pfaffian formula, but I think I had reformulated this as remark 2 last week. This is 1/2 times these evaluations, I mean, these 4 evaluations here. So we have minus Zn 0, 0 plus Zn 0, 1 plus Zn 1, 0 plus Zn 1, 1. Right? This is simply the Pfaffian formula. And now this is less or equal to twice the maximum value of this holds for any theta and tau. So here I might as well write okay, so what have I done? You see I've sandwiched the partition function in between 2 terms like this, maximum of this and twice the maximum. But you see that now if we take if we consider log z, which is by definition this limit here, you see that by these inequalities I can replace the partition function here by this max here. Okay? So I have okay, if I just, I mean, it's clear. I would get log 2 over n squared that then tends to 0. Okay. So far what have I done? I just, basically I used the Pfaffian formula to replace the partition function with this thing here. But of course, the point is that now for these things here, we have some multiplicity formula for Pn in terms of P1. That's what we proved last time, right? We didn't have such a thing for the partition function. It's not true, but it works for this. So now we can use this. Just one remark. Note that this maximum here might depend on n. Right? It might be that for n equal 1, it's 0, 0 is maximum, n equal 2, it changes, right? You have to be careful. Here it's slightly subtle. So which theta tau gives the max might depend on n. Okay, and I just want to write star for this equality because I will use it. Okay, so now, as I said, we can now use the proposition of last week. So we know that, so Zn theta tau, what is it? It's Pn of -1 theta minus 1 tau. And we know by this proposition that it's the double product un equals -1 theta product Vn minus 1 tau of P1, which I write P, of UV. Okay, so if I want to consider the log, well, let's say 1 over n squared log absolute value n, what do I get? I think I already gave a little bit this argument last time. That's 1 over n squared, double sum. And you see that what we get here is a Riemann sum for the following integral for and if you just make a change of variable, you get exactly the integral that I had stated before, so log. And I want to denote this as I, integral I. Okay. So we've put a little bit everything together, the Pfaffian formula, this proposition for the expansion of the fundamental domain. And we have basically, we're almost there. But now what is the problem? So, well, to illustrate the problem, let's just assume for starters that P never vanishes on the torus. Okay, so assume that PZW is different from 0 for any ZW on the torus. Then what do we have? Well, this is a, okay, we have a continuous function. We have, what happens is that here we have 4 different Riemann sums, right, for each choice of theta and tau. And in this case, where the 4 of them converge to the same limit, I, so of course, their maximal here will converge to the same limit as well, and so we're done. Okay? In this case, there is no issue. So then, for any theta and tau, the Riemann sum, the corresponding Riemann sum converges to I. And so we are done by star. Okay? In this case, there is strictly nothing to worry about. So let me just keep this. Okay, now as a second case, I will consider the case where we have a single zero, okay? And I will show you that in this case it's still okay. So now assume that the set of points in the torus where the characteristic polynomial vanishes is just equal to a single point. Okay. So in this case, of course, what can happen is, well, you have, let's say, one of the lattices. So here we have, for each theta and tau, we have one lattice, okay? We have some evaluation on one lattice. We can very well have the case that, I don't know, let's say the 0 is at 1, 1. And so for theta and tau equal to 0, we always have one evaluation here, one of the evaluations that will just lie exactly on the 0. So we have a problem, okay? For the theta tau, this corresponding theta tau, whose evaluation point lies on the 0, or maybe in general very close to the 0, we have a problem. This thing here might not converge to the integral, okay? Again, what can happen is, either we lie directly on the 0 a lot of times, or what can happen is, well, the evaluations on this particular lattice always lie very close to the 0, so it means that this p will be close to 0, so this log will be very small, and we'll have a problem. This Riemann sum will not converge to the integral. Okay. So this can happen, but we are saved. Why? Because actually, this thing here is not equal to the limit of one of them. It's equal to the limit of the maximal of them. So of course, it might happen that one lattice point falls very close to the 0, but the other ones will be far away, far enough from the 0, so that actually so that the maximal thing will converge. You see, and it might very well be that, well, for n, that you will fall. For n equal 1, you fall, it's the first lattice that falls very close. n equal 2, the second lattice will fall close. Then the third, it might go like this. But the point is that, again, here we're taking the maximum. And this maximum here, it's going to be okay. Because we cannot consistently have the 4 lattices falling close to the 0. Okay. That's the argument. So I'm going to write down something for this. So there is one argument that I didn't say for this, is that these evaluations here, they are on 4 different lattices, and these 4 lattices, they are staggered, you see? Meaning they don't, so you see what staggered means. They are not on the same place. So this is also an argument. This is also something that comes into play in the proof. So let me maybe just write something like this. So now note that the 4 lattices, so it's U, V in, so let's say in S1 cross S1, the 4 lattices for theta tau equal to 0, 1 are staggered. So maybe I'll just draw a little something here. Okay, maybe this is for theta tau equals to 0, 0. And then theta tau equal to 1, 0, something like that. And then 0, 1. Something like this, oops. And 1, 1 is the last one here. Okay. So this spacing here is 2 pi over n. So you see that the lattices, they are, if you take little balls of radius pi over 2n, so here radius pi over 2n, they will never intersect. So if you have a fixed, if you have a unique 0 for the polynomial, z0, then you have a unique lattice whose evaluation, well, you have a unique lattice that can fall within distance less or equal to pi over 2n to this point. Okay. So, hence, for each n, there is at most one lattice which falls closer than pi over 2n from z0, w0. Hence, the three others fall further away, and then you can check that if you are further, it's much more than what you need. But if you systematically fall further away than this, then you can check that this integral converges. Okay. Hence, the other three fall far away enough from this 0. So again, I said several times something false. I'm never saying that this thing here converges. This I cannot say. We cannot say that this converges, but we can say that this converges. Okay. For each n, you have one that is good enough, and then if you take this max, it converges. Okay. Hence, converges. Okay? So in Kenyon or Cook of Sheffield, this is not done in full detail, but they refer to an earlier paper of Cohn, Kenyon Prop, where they do this analysis of convergence very, very carefully. But in any case, it's completely fine. So do you agree with me that basically this same argument can be made if we have like 1, 0, 1, 2, or 3 zeros? Okay? So the same argument works if P CW equals 0 intersects the unique torus in at most 3 points. So we're safe in this case. But now let's assume that, let's say that it intersects it at 4 points. A priori, this might happen, right? Then we're in trouble. Now, assume that P of, so let's say, for example, let's say that the 4 real points of the torus are zeros. For example, you take PZW equal Z square minus W square. Okay, so in this case, so this is a case where if I draw the torus opened up like this, it intersects the torus like this. Well, in this case, what happens? Well, then we have Z 0, 0, n is always equal to 0, right? Because in this, we'll always have one evaluation that is at 1, 1. And then if you look at Z, the other 3, it's equal to 0 for any n which is odd, right? Because here, if n is odd, you have one evaluation at some plus 1 minus 1, something. So in this case, we're in trouble because this line that I had written here with the star, this does not converge, right? In this case, so we're in trouble. Of course, here there is a very stupid, I mean, this is a stupid example. I mean, it's smart enough so that we can understand we have to prove something, but it's stupid enough so that we can discard it straight away. Why? Because in this, so we can show that this can never be the characteristic polynomial of a Dimer model. Why? Because here, these things, they are counting, when you take this alternated sum, they are counting Dimers, actually. They're counting, so if you take minus this one plus these ones, you need to have something which is positive, namely the Dimer partition function. So this can never happen in real life, or Dimers. But still, I mean, so this, okay, this one we can discard. We can say, okay, it's fine. It's, this is not going to happen. But a priori, why not have a polynomial that is badly behaved and we can just not conclude, right? So I just write this remark here. Of course, PZW equals Z square minus W square is not a Dimer characteristic polynomial. As we would then have that Zn or Zgn equal to 0 for each n odd. So it means there is something to prove here to be able to conclude. So I will. So there is something left to prove. So I will just write like this because I end this proof, but it's to be continued because we need to prove that if you take a Dimer model on the torus, bipartite, you look at its characteristic polynomial, its intersection with the torus is not too bad. Okay. So let's just try some examples, just to see. So we did compute characteristic polynomials, so let's just check that in these cases at least we're good. And each time we prove that it intersects the torus in a good way, it means in this case we have proven the convergence to the free energy to this integral. So first example, hexagonal lattice. We have PZW is of the form A plus BZ plus CW with A, B, C positive real numbers. That's a very nice and geometric example. Let's try to understand the intersection of this curve with the unit torus. So it means we want to set 0 equal P of E I phi, E I psi, A plus B, E I phi plus C psi. So do you understand these zeros? So we have, so this means what? We take A, and then another side of length B with this angle being phi, and then another side of length C, this angle being psi. Right, this equation here, A, B, C are positive real numbers. And so saying that this has 0 means that A, B, and C are such that we can form a triangle with these 3 lengths. How many triangles can you form with 3 lengths? 2 of them. They're conjugate. Right? And so it means we either have no intersection with the unit torus in case A, B, and C do not satisfy any triangular inequalities. It might happen that we have a single real solution to this the unit torus. It's in case the triangle is flat. And otherwise, we have 2 distinct conjugate solutions. But in any case, we have at most 2, so it's fine. Okay? So here, there are. So I'm just going to say this. So there are 0, 1, or 2 solutions, but okay, there are at most 2, and in this case, they're conjugate solutions to this, which corresponds to the two possible triangles over 3 given lengths. Yeah. I'm sorry? Here? No, I think it's really this angle here, right? I think it's correct. So if I write this as a vector, this is A, and then I have to have B times EI phi, so I'm here, and then I need to have C going like this. So I think it's correct, right? I don't think it's correct to say that it's the defect angle here. I think it's correct this way. So this corresponds to the 2 possible triangles. Triangles with sides ABC. Okay, very good. So it means that we proved that in this case, there is no problem. Let's also try the square lattice. So second example, the square lattice. Okay, again, so let me just write. So 0 equals P EI phi EI psi. And then I had, it was, x squared times 2 plus, so z plus the inverse, meaning 2 cosine phi, plus y squared 2 plus 2 cosine psi. That was exactly what I had in the integral in the example I gave before. So this I write as 2 times x squared 1 plus cosine phi plus y squared 1 plus cosine psi. So is it possible to intersect the unit, so to have a 0 here? Well, so these are all positive terms. This is greater or equal to 0. This is greater or equal to 0. So you see there is a single intersection, and it corresponds to z to phi equal pi and to, yes, phi equal pi and psi equal pi. So it corresponds to, so a single solution to phi equal psi equal pi, which is the same as saying z equal w equal -1. Okay? So here it's still okay, it's kind of tractable. So it works for the square lattice as well, this square lattice. Third example, the square octagon lattice. This was an exercise in homework 9 for today. And you see it starts to become quite difficult. And now, of course, these are the simplest examples, but believe me, if you have not tried this exercise, you just take a big enough domain, a big enough graph in your domain, you compute the characteristic polynomial, then try to compute the intersections with the unit torus. It's hopeless. It's totally hopeless to try to prove directly that this will always behave well. Okay. I will give a fourth example just to see that we have to be a little bit careful when we state a theorem, because of course now there's going to be a general theorem saying that it always works. Let's just be a little bit stupid, and we're going to look at the following graph. Let's put it this way. Okay, if you wish, this is exactly the square lattice with y equals 0. Okay? So, consider the example illustrated opposite. So I don't need, if I want to compute the characteristic polynomial, I can just take this polynomial here and set y equals 0. What do we have? We have P of z w is equal to x squared 2 plus, well, yes. Okay. And therefore, we see that P of -1 w is equal to 0 for any w in S1. So we have an infinite number of zeros on the torus. So this is just to say we have to be a little bit careful, because of course what happens here is that this polynomial is really a polynomial in a single variable. So we have just to be careful and to say, okay, we need our polynomial to be non-degenerate. Okay, so let me I'm just going to write this before the break. So the conclusion of this one is we need to be a little bit careful. So it's a good time to introduce some terminology. So if we have P zw of the form, so a polynomial in these two variables, then I want to write n of p for the so-called Newton polygon of this polynomial. So this is, by definition, this is the convex hull of all the nm in Z such that ANM is not 0. And this means convex hull. So this is called the Newton polygon of P. And then we'll say that P is non-degenerate if the area of its Newton polygon is positive. And so let me just go back to these three examples. The first example we had with the hexagonal lattice. So we have three coefficients that are not 0. It's 0, 0, 1, 0, and 0, 1. So if I take the convex hull of these 3 points, I get this. So this is for the hexagonal lattice. What about the square lattice? So for the square lattice, I had, so now in this form it's not so good, but it was 2 plus z inverse. So I have the coefficient 1, 0, minus 1, 0, 0, 1, 0, minus 1. This is the one for the square lattice. It turns out that if you look at the square octagon lattice, you get the same one. You have one more coefficient. It's the constant coefficient that is not 0. But so there's a point here, but it does not change the convex hull, of course. So here for square octagon, you get the same. And then, of course, if you look at the stupid one here, I have only the coefficients 1, 0, minus 1, 0. The convex hull is a line like this. So this is it's degenerate. Example 4. But you see, you do have to pass to this kind of objects. Even, I mean, these objects will be useful anyway. But otherwise, you can say, yeah, of course. But it just means, there is no W coming, so it's degenerate, sure. But you might, of course, have some W coming and some Z, and still have something that is really depending on only one variable, right? Because it can be that you have, I don't know, ZW plus Z inverse W inverse. In this case, you have these 2 points. And really, if you make a change of variables, you see that there is a single variable. So the right way to formalize depending on 2 variables is this way here. I guess you agree. OK. And of course, the theorem that I'm going to state right after the break is if you start with a non-degenerate, well, with a Dimer model that is non-degenerate, then the spectral curve, the 0 of the characteristic polynomial, intersects the torus in at most 2 points. And therefore, everything works. Okay. So let's make 15 minutes break. And at 20 past, I resume. OK, maybe just one remark that came in the break. What does it mean to be non-degenerate? Can we understand this geometrically in terms of Dimer configurations? And indeed, relying on one exercise that we did, I think last week, you can see that a Dimer model has non-degenerate spectral curve or a characteristic polynomial if and only if when you look at the composition cycles made by the difference of two perfect matchings of two Dimer configurations, then you realize two non-trivial homology classes on the torus. Okay, for example, here you obviously see that the only non-trivial homology class you can realize is the one going in this direction. But as long as you realize two non-trivial homology classes, then you're non-degenerate. It's equivalent. But it's not something, I mean, of course, this example is stupid, you see it immediately, but it's not something that, it might very well be that you have a graph that is very complicated, very big, to some extent, but it turns out that you can never realize, you can never cross neither in this direction nor in this direction using, difference of Dimer configurations. So this could happen, but okay. Okay. So now I can state the theorem. So there are two published proofs. I'm going to say a little bit more about it at the end of the class. But basically, I will attribute it to Kenyon-Okounkov. There is also a proof in Kenyon-Okounkov-Sheffield, but they wrote a separate paper, just Kenyon-Okounkov, where they give another proof of this theorem. For any toroidal bipartite graph with non-degenerate characteristic polynomial, the intersection, so the set of ZW in S1 plus S1 such that PZW equals to 0 has at most two elements. And in this case, they're conjugate. Again, this is a very deep result, and there is no way to prove this by brute force. I mean, of course, I cannot prove there is no way, but if you try, it's just very difficult. So, and of course, now I hope I motivated this statement enough that you find it interesting, but actually this statement then will have a lot more consequences that we're going to see next time. So, I am not going to prove this theorem. That's really beyond the scope of this class. But I want to explain a little bit in which way they proved it. And also because, again, I put the emphasis in this class on the variety of tools coming into play. And here, there's a new tool coming into play, namely real algebraic geometry. So I want to say a little bit about this. So no proof in this class. But some ideas of the theory behind it, behind the proof, namely real algebraic geometry. In which I am by no means an expert, but I know just enough to explain to you a little bit why it's really quite an amazing result. So that's a little detour that we're going to make basically during the end of this class. So it's the paragraph 3.4. Amoebas and Harnack curves. Okay, so fix a polynomial PZW with real coefficients. We have the following terminology. So I want to denote C of R to be all the zeros of this polynomial. So this is the associated real curve. It's an algebra, well, we can say plane curve. Okay, so you really have to think, well, it's really a curve. In the plane, here in the plane minus 2 axes. And then you can also look at the complex plane curve. Is the associated complex plane curve. So you still see curve, but now it's a complex curve, so really topologically it's a surface. Okay. So it's a surface in the two-dimensional complex space, so four-dimensional real space. Okay, and so one of the central objects of this theory is the so-called amoeba. The amoeba of P is the image AP of C under the so-called amoeba map, which we can denote like this. Log goes from C star square to R square, and it maps ZW to log Z log W. So this apparently was, this amoeba stuff was introduced by Galfand, Kapranov, Zelevinsky, sorry for the pronunciation, in 1994. And completely amazingly, what will happen is that if you start with a polynomial, it's a characteristic polynomial of the Dimer model, then the amoeba will give you basically the phase diagram for the model. I will talk about this next time. It's quite amazing because there is a whole theory of real algebraic geometry, and every object that they define in this theory corresponds to something for the Dimer model. It's quite amazing. What do I want to say here? Remark. So, 12 remarks. Okay, first note that we have that x, y belongs to the amoeba of P if and only if P of EXZ, well, EYW equals 0 intersects a unit torus. This you can check directly. So in particular, remember that we are interested in the intersection of this with, so we are interested in knowing if the point 0, 0 belongs to the amoeba. This would mean that PZW equals 0 intersect the unit torus. And we're interested in knowing how many points, if the origin lies in the amoeba, how many points here will be mapped to it. Okay? In particular, we are interested in knowing how many points of C are mapped to the origin. That's the number of intersection of the spectral curve, the complex curve, with the unit torus. Okay. Second remark, note that if PZW is equal to 0, then 0 is also equal to the conjugate of all of this. Since P has real coefficients, this is P of Z bar W bar. So you see immediately that if you have a point in the complex curve, then its conjugate is also in the complex curve. Okay. So you see in particular that if the amoeba maps is one-to-one at some point, then this point must be real. Must be a point of the real curve. Okay. Hence, so the places where the amoeba map is one-to-one are on the real curve. Okay. So let me make a couple of examples. Obviously, I'm going to take always the same ones. But to be a little bit more, so for this to be a little bit easier, I'm just going to set the weights to be equal to 1. Okay, we'll just remind you what the Newton polygon is in this case. And I want to sketch the amoeba in this case. Okay. So for starters, let's just assume that x equals 0. X equals 0, this means that Z has modulus 1. So now I want to understand the intersection of the amoeba with the y-axis. I want to see for which W can I have this equal to 0 for norm of Z equal 1. So now we have 1. Then I have a Z. Then I only know that it has norm 1. And then we want to understand what kind of modulus of W I can realize for closing this triangle. And you see that what you have, it works if and only if, well, the modulus of W, we can make it as small as possible. Okay, we can always realize this. And then we can go all the way to 2. So it means that the intersection of the amoeba with the y-axis is between minus infinity and log of 2. And you see that whenever the norm of W is strictly between 0 and 2, the amoeba map is 2 to 1. So we have two possible triangles. And when W, the number of W is equal to 2, then we have a single one. So here, I'm just going to write log of 2 somewhere. And the intersection of the amoeba with this axis is something like that. And maybe I will try, what I will do is I will write this in another color, saying that for this, the log is 1 to 1, the amoeba map. So is 1 to 1, and for blue, it means that the amoeba map is 2 to 1. And then you can do, of course, so by symmetry, you can do the same for the other axes. Something like that. And then actually, so you can try a little bit, and you will see that there is another axis where it goes to infinity, and eventually you get something like that. Hence the name amoeba. So now do you see, so it's a very natural way to try to picture yourself the spectral curve, the complex and real curve. What do we see? We see the complex curve, that is the surface, is given as follows. You put 2 points above each of the blue point here, and you put 1 point above each of the green points here, and what do you see? You see a surface, right? You see the surface. Do you see it? You don't seem to. You take 2 sheets, 2 copies of this kind of triangle, and you glue them along the green boundary. And you have a surface. It's actually a sphere. Well, if you compactify, it's a sphere. So this is a rational curve. It's a rational curve because the complex curve that you get is actually a sphere. This is a rational curve. Topologically, it's a sphere. So, okay.
So the fact that it's a sphere for some algebraic, like, implies that it's rational for some strange algebraic geometry reason, or back to the geometry?
Yeah, the answer is yes, but yeah. So you have a rational parametrization of your surface. So rational does not mean linked to the rational numbers. It means you have a parametrization by rational functions. Okay, that was one example. So I'm not going to make too many computations because there are some facts that allow you actually to draw the amoeba from the Newton polygon. So here, can we guess it already? Maybe not yet. So let me put one more example. Obviously, I'm taking again the square lattice, this time with okay, I'm just setting the weights to be yeah, I think that's correct. Okay. That's correct. Okay. What is the So when I had done this example the hour before, I had forgotten to mention this point here, but anyway, it doesn't change the convex hull. This is N of P. And let me draw for you the corresponding amoeba. So it will go like this. And I'm not being completely precise here. Actually, here in the middle, we know that the amoeba map is 1 to 1. Remember? We have seen that it intersects the unit torus in a single point. So here I also have the green point. Okay? In this case, this is a singular curve, singular surface. You see there is, so do you see it? It's like a sphere, but it pinched at one point. So this is a singular curve. And the third example is given by the square octagon lattice. And in this case, the Newton polygon is the same, but the amoeba is nicer. Do you see the surface? This time it's a genus 1 surface. Okay. So, okay, I hope I'm able to finish this. So what I'm going to do now is just mention to you some known facts about amoebas. And I'm not going to, of course, not going to prove them. And they are due to several different authors. The three authors that I mentioned before, and then also Mikhalkin, who is a professor here, a specialist of these questions. So if you have further questions about amoebas, you should ask him and not me. So let me mention these facts. An amoeba has several tentacles. Doing like this. So each tentacle contains a unique ray. And narrows exponentially fast towards it. What is nice is that you can actually, the rays correspond, well, the directions of the rays correspond to the sides of the Newton polygon, as you might have guessed from the examples. So each ray is orthogonal to a side of the Newton polygon and is directed towards an outward normal direction. The outward. Okay, here we see it. We have these 4 different tentacles corresponds to 4 rays. These 4 rays, they are orthogonal to the sides of the square. Okay. Now, how many of these do we have? Well, these examples are a little bit too simple. In general, so here you see that we have 1 tentacle for each side. But what happens is that in general, the sides might intersect the Z2 lattice in a certain number of points. And the maximal number of tentacles is exactly given by basically these points, this number of points. So let me be more precise. So for each side, let's say delta I of NP, and I want to number the sides like this. So there is at least 1 tentacle, and at most, how many of them? So DI which will be my notation for the number of intersections of this side -1. So in this case, it's very easy. You have, for each side, you know that you have at least 1, and you know that you have at most 2 minus 1, 1. So in this case, there is nothing to say. But what might happen in general is that, again, this thing intersects Z2 in a certain number of points. And for each interval between 2 points, you have one tentacle, and they're all parallel to each other. Okay. So now we understand these tentacles kind of well. And what about these bounded components here? Each bounded component of the exterior corresponds to one point of, so they correspond to the points in the interior of the Newton polygon. So integral point. Hence, there are at most, I will denote by G, this number of points. Okay, in the third example, it's exactly what happens. We have 1 point inside, it corresponds to one bounded component. In the first example, it works as well. We had 0 points inside, we have no bounded components. And in this example, well, that's a singular one. So this really counts as one bounded component, but okay. It's just, you should imagine this bounded component being shrinked to a point here. So it's a singular curve. And the last fact that I need here, that the area of an amoeba, so of course they're not bounded, but actually they are a finite area, and they're bounded by pi squared times the area of the Newton polygon. So now I have a little issue with time. I have 10 minutes and I don't. So what I want to do is somehow define these Harnack curves. Anyway, it's going to be a very vague definition, but let me try to do it. And anyway, it's just to give you some idea. So this motivates the following vague definition. So first, I need a little construction. It's to say that each Newton polygon defines a compactification of r star square by adding S, so number of sides, real lines L1, Ls. So, and maybe I'm going to make a little illustration here. So here, typically, what I want to add is you should think of what you add as kind of lines that are parallel, at infinity, that are parallel to the sides. Okay. Then one can consider the closure C of R bar of the real curve in this compact space. This is just to say, for example, in this case, let's see here, then really I will have a real curve that is really going to be a certain number of components, and really it's going to be one component here, and then here a single component here that will go like this, then touch this axis once, go back here, touch once, etc., like that. It's just that we want this big thing here to be a single component of the real curve. Okay, and now here comes the really vague definition. C of R is a, sometimes it's called special Harnack curve, but we're just going to say Harnack curve for now. If the following holds. First, we want it to have the maximal number of components. How many components can it have? It can have, it can have one component for each point inside the Newton polygon, so I named this G. And then it can have one more component that goes outside like this. And really what we want is that it has the behavior that we have seen so far. That is, we have G components that do not intersect these new axes. And we have a single component that intersects all these new axes cyclically and in exactly the maximal number of times, that is D1 time for one, D2 for the second, etc., etc. So exactly the behavior we've seen here, except that I didn't show an example where I have di being greater than 1. So the G is here, it's not there, so let me just write this. Is a special Harnack curve if this compactified curve has the maximal number of components, that is G plus 1 components, or we call them ovals components, i.e. the maximal number. Only one of them and it does so maximally, again, i.e. D1 times L1, then D2 times L2, etc. So let me make just an illustration and then maybe also an illustration of what is not allowed, typical behaviors that are not allowed. So okay. So I'm starting with the Newton polygon. Okay, in this case, what do we have? So in this case, we have G equal 1, 2, 3, 4, 5, 6, 7, 8. It's way too much. So maybe the D1 is 1, 2, 3. So each of them is 3. So the behavior that I want to have for the amoeba is something like this, 1, and the same for each sides. Okay, so, and then how many do we have here? 13, way too much again. So again, you have the right number here. Okay? So here you have D1 equal D2 equal D3 equal D4 equals 1. And if I'm not mistaken, G is equal to 13. And so this would be the amoeba of a Harnack curve. It seems to work because, indeed, I have exactly G plus 1 components. I have G of them that do not touch these new axes. And then the last one, it touches the axis, but exactly in the right number of times. And right, OK. Now here's the theorem of Mikalkin. Sorry, I said I wanted to show something that is not allowed. Typically, something not allowed would be something like that. Then at some other point, something like this. OK. Because in this case, it would not intersect the axis cyclically as we want. Okay. And you notice that if this happens, what would happen? Then you would have a place where the amoeba map would not be 2 to 1. It would be maybe 4 to 1 here in the middle. And also, it seems that then the amoeba would not have maximal size, maximal area, right? So all of these remarks, I hope, make the following theorem of Mikalkin kind of intuitive. The following are equivalent. First, CR is a possibly singular, like the one we saw before for the square lattice, Harnack curve. 2, the area is maximal, that is pi squared times the area of the Newton polygon of the amoeba. It's pi squared times the area of the polygon. 3, the amoeba map is 2 to 1, is at most 2 to 1. Corollary. If P defines a Harnack curve, then the amoeba map being 2 to 1, in particular, it's 2 to 1 on the point on the origin. So it means that the corresponding spectral curve intersects the unit torus in at most 2 points. Okay. If P defines a Harnack curve, then I have not introduced this terminology, but we call this a spectral curve, the corresponding spectral curve intersects the unit torus at most twice. It says much more than this. It says it intersects any torus at most twice. That's exactly the statement, the third. The third statement is exactly saying the spectral curve intersects, well, a curve is Harnack if and only if it intersects each torus at most twice. But of course, what we need for now is just intersecting with the unit torus. And now I can rephrase the theorem of Kenyon and Okunkov. If P is the characteristic polynomial of So and we assume it's non-degenerate, of a Dimer model. Then the spectral curve is a Harnack curve. And again, obviously, I'm not going to give the proof of this theorem, but I did want to pass through this thing because actually in this paper, the way they prove this is really using the vague definition that I gave. So they're really proving by hand that it satisfies these properties. You have the maximal number of components. They intersect these things. It's quite amazing. What they do first is that they use some local moves to say, okay, if you start with a Dimer model, with a biperiodic Dimer model, then you can, via some moves, you can always say that actually you have an hexagonal lattice, but with big enough fundamental domain. Then when you are on the hexagonal lattice, the compactification here is very simple. The compactification is simply the real projective plane. And so you have only 3 axes, and then it's easier to deal with. But there is a second part in this theorem. Well, they proved 2 theorems in this paper. Moreover, every Harnack curve can be realized in this way. And this is really spectacular because now it means that actually this theorem goes both ways. And if you're interested in the Dimer model as we are, then we can use real algebraic geometry to prove things like we did and like we will do next time. But actually this means that if you're interested in Harnack curves, then you can use the Dimer model to study them. Because you can say, okay, actually you can parameterize Harnack curves using Dimer models. And they have really explicit constructions where you start with some Newton polygon, and just from, that's in another paper, but from the Newton polygon, you can really construct explicitly a Dimer model on the torus whose spectral curve will be a Harnack curve with this specified Newton polygon. And I think that was the first explicit construction of a Harnack curve for each Newton polygon. So it's really amazing. So it's an incredible interplay of statistical physics and real algebraic geometry. And it's, of course, among other reasons for this achievement that Okunkov got awarded the Fields Medal like the year after that or so. Okay, I think that's all I wanted to say today. Sorry, I went over, but I think it didn't make sense to stop before the end. Next time, so it's the 11th week, I'm going to give one last class on the Dimer model. It would really make sense to actually finish the year with the Dimer model, but I do want to say some things about the Ising model, so I'm going to just do a very kind of summary of the rest of the theory, well, part of the rest of the theory next week. And then we'll have 3 weeks left for the Ising model. And one small last announcement for the exercise that I was starting now in 10 minutes. I asked, there is a student who actually programmed some pictures of the height function. So if you did the exercise of last week, homework 9 or 8, I don't remember, on the height function associated to square lattice or hexagonal lattice, he actually programmed some nice pictures. So maybe you're just going to take 5 minutes at the beginning of the class. He will show you this because it's very nice to see these pictures. Okay, have a nice week.